talk a little bit about Kepler's third law of planetary motion, or the harmonic law. We're going to use two different versions of that in this class, and I'm going to start off with the simple form as deduced by Kepler for the motion of the planets in the solar system. And in that form, the simple form, Kepler's third law tells us that the period squared in years is equal to semi-major axis of the orbit of the object cubed. So p squared equals a cubed. So drawn out an orbit here that's pretty close to circular, and if it's a circular orbit exactly, then semi-major axis is just the radius of the circle, and in general a bound orbit is going to be an ellipse, and so the semi-major axis is half of the distance of the long axis of the ellipse. It's on average how far away the object is from the sun. Using the simple form of Kepler's third law, we have a few restrictions that we need to keep in the back of our mind. First off is about the mass that is causing the orbit. So either the object is directly orbiting the sun, or it's orbiting something with roughly the same mass as the sun. And we need that restriction because everything is tied to having a solar mass worth of gravity pulling on the object, causing the orbit. If that is, restriction 1 is not satisfied, we're going to have to use the general form of Kepler's third law, which is a little bit more complex but has the same basic structure of period squared is going to be something times semi-major axis cubed. We'll go to that here in a little bit. The other restriction, the period P, is in years. If it's not measured in years, you're going to need to convert units to make it be a period in years. And the semi-major axis, A, in astronomical units. And again, if it's not in AU, astronomical units, then you need to change units to go from whatever it is measured in into AU. All right, so let's look at a few examples of applying this. So first case is what do we do if it's the period we're trying to solve for, so the period is unknown. So basically, given a semi-major axis, what's the period? So period squared is semi-major axis cubed. I'll clear the square by taking a square root of both sides, and that's going to give me a period is equal to the semi-major axis to the 3/2 power. So an example. So how long is a year for the asteroid Ceres, so the largest of the main belt asteroids? And for Ceres, the semi-major axis, you can look it up in the appendices, 2.77 astronomical units. Or AU, if you rather. Okay. Now, the simple form of Kepler's third law is set up such that if this is the number in astronomical unit, then P comes out as the period in years. So that's an Earth year. So P is going to be A to the 3/2 power. We just put in the 2.77 to the 1.5, that's 3/2, and that tells us 4.61. So the period equals 4.61 years. All right, let's try another example with an unknown period. So example, innermost planet Mercury. There's a semi-major axis of about 58 million kilometers. How long is a year for Mercury? How long does it take to orbit the sun once? All right, so again, like with Ceres, we are orbiting the sun, so that part's good. 58 million kilometers, that is not in astronomical units, so we're going to have to change that into astronomical units before we can use the simple form of Kepler's third law. So 58 million, 5.8 times 10 to the 7th kilometer, and 1 astronomical unit is 1.5 times 10 to the 8th kilometer. So just multiplying by 1 to change the units. And we see that this is set up correctly because the kilometer cancels out, and we're going to be left with A, an astronomical unit. And when we do that, we find semi-major axis for Mercury is 0.39 astronomical unit. All right, so now we're ready to use simple form of Kepler's third law. Unknown period is going to be P is equal to A to the 3/2 power. And this is in astronomical units, so I can just plop in 0.39 as a pure number. 0.39 to the 1.5 power. And when you do that with your calculator, you'll come up with 0.24. And we can answer our question. Year for Mercury is about 0.24 Earth years. All right. The other way we can use Kepler's third law in the simple form is when you have A is unknown. So an unknown semi-major axis. So given a period, we want to find the semi-major axis. So I'll have A cubed is equal to period squared. I clear the cube by taking a cube root of both sides of the equation. I haven't changed the equation because I'm doing the same thing to both sides. So the cube root of A cubed is just A, and the cube root of P squared is going to be the period to the 2/3 power. All right, so let's try an example with that. What is the semi-major axis Halley's Comet. Given its orbital period of 76 years. Alright, so the period is already in years. Halley's Comet is orbiting the Sun, so we're good to go with a simple form of Kepler's third law. So A is going to be P to the 2/3 power. This is in years, so I just pop it in as a pure number. 76 to the 2/3. And same thing as 76 to the 0.67. It's going to give me 18. So semi-major axis is 18 astronomical units. All right. Do another example with a unknown semi-major axis, known period. So this is the case of the planet 51 Pegasi b. So first planet discovered orbiting the star 51 Pegasi. It's also the basically the first normal-ish extrasolar planet discovered. So 51 Pegasi b has an orbital period of 4.23 days. What is the semi-major axis for the planet's orbit? And we're given an additional piece of information in this example. 51 Pegasi is basically a solar type star. Okay, so let's go through our little checklist. We're trying to find the semi-major axis. If set up correctly, that will come out in AU. We have a period that is 4.23 days. That is not in years, but we can convert that pretty simply. And we know that the mass is about the same mass as the Sun, because 51 Pegasi is a solar type star. So let's convert the period first. 4.23 days. And 1 year is, to that precision, 365 days. I only know 3 digits out of that, so I'm not going to worry about the other digits to make up the other fraction. Whoops. So day cancels out with day, and we're left with the year. And that's going to give us 1.16 times 10 to the minus 2 years. So we have a period in years, and we can use the simple form of Kepler's third law. So semi-major axis is period to the 2/3 power. I'm going to plop in 1.16 times 10 to the minus 2. Raise that to the 2/3 power. Going to give me 0.0512. And that's going to be in astronomical units. 51 Pegasi b has a semi-major axis, a 0.0512 astronomical units. that's remarkable. That's a very small semi-major axis, even compared to what we had for the planet Mercury before. This planet is very, very close to its parent star, a very tight orbit. I'm going to talk about a couple of extensions thinking about this. So I'm going to draw out a little orbit. So a pretty eccentric orbit there. And there's one foci. We've got a perihelion distance, and the furthest away that a planet is in its orbit is going to be the aphelion distance. And then I'll show you how you can calculate those given the eccentricity of the orbit. And the eccentricity E is going to vary between 0 and 1. A circular orbit has no eccentricity, so it's a value of little e of 0, and then a elliptical orbit that has basically shrunk to be like a line. It's the most eccentric orbit possible that will have an eccentricity of 1. So greatest distance from Sun in that eccentric orbit, that is the aphelion distance. So d sub a is going to be the semi-major axis times 1 plus the eccentricity, and the smallest distance from Sun in an eccentric orbit is the perihelion distance. So d sub p is again the semi-major axis times 1 minus the eccentricity e. And again, if it is a circular orbit, then e is 0. The aphelion distance is the semi-major axis. The perihelion distance is the semi-major axis. All the distances would be the semi-major axis for a circular orbit. All right, and then one last extension for Kepler's third law. So what do you do if the object that is causing the orbit is not the Sun, or something that has the same mass as the Sun to cause that same amount of gravitational pull? Well, then we have to use the general form of Kepler's third law, which was developed by Newton. So Newton's form period squared is equal to, now we pick up some constants, 4 pi squared, semi-major axis cubed, so it still has the p squared and the a cubed. And then in the denominator, we have a new constant of nature, universal constant of gravitation, and the sum of the two masses of the bodies involved in the orbit. So let's go through what all these are. So P is orbital period in seconds. A is the semi-major axis in meters. M1 and M2 are the masses of the two bodies in the orbit, and that is measured in kilograms. And G is a constant of nature. Newton's universal constant of gravitation, 6.67 times 10 to the minus 11. It is meters cubed in the numerator and kilogram times seconds squared in the denominator. So I have some other examples of doing calculations with the general form of Kepler's third law, but I did want to point out this is what you need to turn to if you can't satisfy that first restriction, that the object that is causing the orbit is the sun or has the same mass as the sun. If it is some other thing like a black hole or an entire galaxy that's causing the orbit, then the mass is clearly not going to be the mass of the sun, and we have to revert back to the more general expression. So a little bit more complicated to use because it has more terms in it, but at its heart, it does still have this proportionality of period squared is going to be proportional to semi-major axis cubed.